for joining us. It's an honor and a privilege to be able to share with you today and talk about solids and drilling fluids. I see a lot of very familiar names on the attendee list, so good to see you again, at least virtually, especially in this most unusual time in our world and in our industry. And so today we're going to talk about drilling fluids and specifically around solids and drilling fluids. And a lot of the concepts and the terms and the details around solids we do talk about in the Drilling Fluids Technology course, which PetroSkills teaches. But today I just want to talk about solids, and I want to talk about some of the concepts around solids that come up in a lot of conversations, a lot of details with operators, etc., about how do we drill more efficiently? How do we make sure that we're drilling the best wellbore that we can? And so we thought we would do this today and just have kind of some open question time here at the end. A little bit about myself. I am an employee of PetroSkills. My role at PetroSkills is I'm the Director of Technical Division Operations, and that means I take care of our discipline networks as well as our communities of practice. And I'm also the instructor for our Drilling Fluids Technology course, which many of you on the call have taken. At 18 years with Halliburton as a mud engineer, as a fluids technical advisor, moved over into learning and development and supported the competency implementation, etc. As I said, I teach drilling fluids. I also teach solids control as well as well design engineering and drilling practices. And if you would go out to the PetroSkills website, www.petroskills.com, you could see many of those courses and get a little bit better idea. We would love to have you in one of those as well. So let's kind of talk about solids and let's dive in. And as we go through this today, I will give you a little bit of a heads up at the end of the presentation. My goal is that we are going to play a game of Kahoot. If you're familiar with Kahoot, you know it is a web browser-based kind of question and answer time. We are going to be playing that at the end. I will give you directions to that when we get to that point. So be prepared to have an extra browser window handy, ready to jump on to play along with us. So let's talk about our objectives this morning. What do we want to share in the next hour or so? We want to talk about good versus bad solids in a drilling fluid. I often get this question as we present drilling fluids technology, as I talk with operators, as we're taking care of fluids at a well site. Well, what are good solids and what are bad solids? And we're going to talk about that today, what we mean by good versus bad solids. We also want to be able to understand different classifications of solids. Why do we classify solids, and why is it important for us in a drilling environment? I'm going to share how we calculate the solids content and the types in a drilling fluid. We're going to talk about what happens as solids accumulate in a drilling fluid and in a drilling scenario, and what can happen if they go unchecked. And then we're also going to talk about specific properties of solids as we go through today, and what questions we should be asking. When you read a mud report or you're presented with a mud report, what's important to know about solids? What should be going through our mind when we read one? What are what I call unrealistic numbers around solids? What are fuzzy numbers around solids? And we'll talk about that here today. So let's go ahead and dive in. And the first thing is I want to talk about how solids act in a drilling fluid. We know that in a drilling fluid, it is composed of many, many different things. We have barite, we have bound water, we also have what we call free water. We have emulsified liquids, and as we're showing up here, we have gas, we have drill solids, polymers, hydrated clay, and these drill solids begin to interact with all the different components of a drilling fluid. And it doesn't matter if it's a water-based drilling fluid or if it's a non-aqueous phase fluid, or what we have commonly in the past called a invert emulsion fluid or an oil-based mud. Those solids play an important part in those systems, so we have to understand what these solids do and why are they there? What is the the components of it and what do we need to be looking for. And that's what I want to focus on today as we talk about in the drilling fluids class. We often say that fluids are the lifeblood of the operation. And that is absolutely true, but solids play a very, very important role in that. And the reason that it plays an important role is different types of solids perform different functions. So we basically look at solids and we say, okay, is it a commercial solid or is it a formation solid? So today during this webinar, as I share the word commercial solid, I am talking about a solid that we intentionally put into the drilling fluid and we add it to accomplish a purpose. Okay, somebody is paying to put those solids into the fluid. Normally when we think about this, we think about weight material. Of course, barite comes to mind to help increase the density of our fluid. We also know that we add solids to help improve our rheology. Typically, we speak about bentonite or bentonitic clays for a typical water-based mud. If we're talking about some of the more salt systems, we're talking about some of the adipolgite clays, etc. But we use these solids to help enhance the rheology. We also use solids to increase lubricity, and this is one that we don't often think about, but when you think about lubricity and solids, you instantly need to start thinking about drilling beads. How do we slide in and out of a wellbore? We also have solids that are what we call dissolved solids, and dissolved is probably a little bit of a misnomer because they're solids when they're on the surface, and once we add them to the system, then they dissolve. Right? We talk about salt. Salt will go into solution. It'll solubilize in water. We talk about caustic. We add caustic to our system, then we mix it with water. And any of the other chemicals that really are solubilized. On the surface, they are a solid. If they are not completely solubilized in a fluid system, well, then we'll still have an increase in those solids content from them as well. And then, of course, lost circulation material. If we start losing fluid to formations, we add the lost circulation material to that mud. Those are commercial solids. Somebody is paying to put those solids into our mud. We also have formation solids. And formation solids essentially are any solids that we pick up into our mud system from downhole. Some solids can cause a loss of viscosity control. Some are very, very abrasive solids, can damage the tools in our circulating system and our drilling tools. Sometimes in a very dramatic case, we talk often about such rocks as pyrite, fool's gold, and pyrite will destroy drill bits. And so that's one of them. The other problem that we really have with formation solids is very high filtrate losses. And the reason for this, as we often talk about, is solids that are generated in the wellbore are oftentimes very angular. They are non-uniform. So when we try to build good wall cake with formation solids, the wall cake isn't very stable. It's not very consistent. And thus we have very high filtrate losses into the formation when we try to build a filter cake with formation solids. And we know that they build a very thick, very sticky wall cake with lots of fluid loss. And of course, anytime we have a very thick, sticky wall cake, we increase our chances for stuck pipe. And so those are two kind of high-level categories. I'm going to spend some time here in just a minute diving more into those and kind of talking about the different characteristics that we see. But generally, we talk about commercial solids. Again, somebody is paying to put those solids into a fluid. And we talk about formation solids, solids that are generated from the wellbore. We drill a formation. The solids are drilled up by our drill bit, and they are incorporated, hopefully not for long, into our fluid system, and then we remove them at the surface. So with that, let's kind of talk for just a second about what happens with these solids. What are the impacts of solids in a drilling fluid? Very, very high level, and today we only have an hour together. We're not going to be able to talk into the details of these. We talk about many of these details, again, in our Drilling Fluids Technology course. I'd love to have y'all attend that with us, either virtually or hopefully when things turn around in our industry and our world face-to-face again, but we talk about these in quite a bit of detail. So when we talk about solids, remember that solids have a specific gravity. And I always start that at the very base level in any class, any discussion, because oftentimes I think we forget about the fact that solids do have a specific gravity. And when you add those solids to any drilling fluid, the overall density of the drilling fluid will increase. Most of the time, this is in a very positive aspect. And so I have that colored in green here on our screen. We want to increase mud weight, of course, because it creates wellbore pressure and it helps to balance formation pressure. We're holding back the gas and the other pressures that are coming in from that formation. We know that when we have an increased amount of solids, we also have a higher ECD. All right, because when we increase the solids, we're increasing the density of the fluid, which creates more pressure, particularly in the annulus of our wellbore, so we have higher annular pressure losses, and thus we have a higher ECD on the bottom of the hole. This is particularly important if you're drilling wells that you have very, very high rates of penetration. And the reason being is because as those solids accumulate in the annulus section of your wellbore, remember that the density in the annulus coming up from downhole is not the density of the fluid that you are pumping down inside the drill string. It is higher. The reason it is higher is because solids are now adding to the overall hydrostatic pressure, that is the density of the fluid on that backside. So we have a higher ECD. Whenever we have a higher number of solids in our fluid, we also have an impact on the rate of penetration. And this is a negative rate. We have a decrease in our rate of penetration. And for the most part, it kind of goes without saying, but I'll make a few comments about it, is that remember that those solids, incorporating this into the system, they don't allow us to drill better. It is a thicker, it is a clunkier type of fluid, and thus our rates of penetration will decrease. As you look back over history and you look at different metrics around drilling, folks that have studied this for years will tell you that if you can drill a well with pure water, do it. Always try to drill it with pure water. But the fact is, we can't, right? We've got to have certain chemicals, we have to have solids, et cetera, to be able to drill certain depths, hold back formation, and to be able to treat our mud. So we have a decrease in the rate of penetration. Because we have solids in our fluid, we also have increase in surge and swab pressures. Remember that surge and swab pressures are the pressures that are induced when we are tripping into the hole and pulling out of the hole respectively, surge and swab. And the reason for this is that you're drilling a wellbore with a certain size drill bit, and that is the size of the hole, and the bit just barely fits inside that hole, and so we have this plunger effect. When we pull out of the hole, we are essentially creating a low pressure system beneath the bit, and we are pulling formation fluids into that low pressure system. And as the fluid gets thicker, as there are more solids, the weight increases. It's harder to maintain those surge and swab pressures because the pressures increase. And the opposite is also true. We have a thick fluid with lots of solids in it, very high density. As we start tripping into the wellbore, that plunger effect creates a higher pressure beneath the bit. The fluid cannot escape around the bit quickly enough, and thus, if we're not careful, we risk breaking down the formation and losing returns as we're tripping into some of the more weaker formations. We also have an increase with differentially stuck pipe. As we talked about earlier, is that formation solids, as we try to build formation wall cake with it, the wall cake is not very consistent. It's not smooth. It's very rough. It has a lot of gaps in it, and thus we have fluid loss to the formation. And if we have fluid loss to the formation, we have pressure that is escaping out to the formation from the wellbore, which means we have a risk for differentially stuck pipe and pulling the drill string over to that thick, sticky wall cake that we've been talking about. Chemical reactions is also an interesting one, is that as we intentionally add commercial chemicals to our drilling fluid, the increase in the number of solids in that fluid will decrease how fast our chemicals will react with water. For instance, if I were to put in a deflocculant, or I were to put in a thinner, or I were to put in a chemical, the chemicals take a little bit longer to react because there are solids in the fluid. Whether those solids are inert, meaning that they don't do any reaction, they don't react with anything themselves, or if they're highly reactive, it slows down those processes by having an increased number of solids in the fluid. Running casing and cementing casing are two excellent categories to talk about. We have a high increase of the chance of problems trying to get casing down to bottom because the fluid is thicker. I've heard the expression recently, it's like trying to push toothpaste, trying to get casing down to wherever it's at prior to cementing, and then pumping the cement itself back around. And that is why whenever we land our casing, we always want to circulate the wellbore clean, get all the solids out. If we've knocked some off the formation as we went down into the wellbore, anything that was left that we didn't get out the first time, we want to circulate those out and get them out of the mud as quickly as possible, preferably at the shale shaker at the first available opportunity, so that we get a good cement job and we can continue drilling on, or if it's production pipe, be able to produce the well. And of course, then if we have an increase in ECD, we have an increase in pressures, obviously our pump pressure is higher by the increase in solids. It is a more dense fluid. It's a heavier fluid. And so that creates some issues for us, which we'll want to make sure that we address with the increase in solids in our fluid. So I want to show you a little bit of a chart here. And again, as Clay mentioned at the beginning of the session, we are going to be distributing these slides, so don't worry about trying to copy all these down right now. You will have these, but I also wanted to show you in a graphical representation, what do these solids look like? And so if we start over here in the left-hand side, you will see our commercial solids. And I'm going to bring my cursor up here. And I'm going to bring my pointer so that everybody can follow me. Annotating. Well, yeah, we'll just do it this way. Let's do it manually. So on the left-hand side of the screen here, we have our solids. And let's start with the commercial solids. And again, the commercial solids are solids which have been intentionally added to the mud, to your drilling fluid. They may consist of our low-gravity solids, which we have over here on the left-hand side, or our high-gravity solids. When we talk about commercial low-gravity solids, we basically have two categories. We have our non-reactive solids, and we have our reactive solids. So let's talk about reactive versus non-reactive real quick before we go any further. A non-reactive solid is a solid that we put into the fluid, into our mud system, and we don't anticipate a chemical reaction. We don't anticipate a transfer of electrons. We don't anticipate shared electrons, etc. in those fluids. They're non-reactive. When I think about non-reactive solids, I think about lost circulation material. I think about lubra beads, beads we put in to help us slide in and out of a wellbore, particularly in a deviated wellbore. And so those are non-reactive. Anything on the lost circulation side, mica, fiber, all of those really don't have a chemical reaction. They're there for the physical plugging of a wellbore, etc. So they are non-reactive. All right. On the opposite side of that, we have what we call reactive low-gravity solids. And reactive low-gravity solids are good low-gravity solids. What do I mean by a reactive low-gravity solid? A reactive low-gravity solid performs a function for us in the wellbore. Most commonly, we talk about bentonite, and I have bentonite down here in green in this box. Sodium montmorillonite, probably the most common viscosifier of clays that we have in drilling fluids. That is a reactive commercial low-gravity solid. We intentionally add that to our fluid to increase our rheology, to increase our viscosity, to help build wall cake. Those are good solids. We also have reactive low-gravity solids that are the solubilized ones that I've already mentioned, the salt that we add to the system for salinity. We may add caustic for pH and lime for alkalinity also in our system. So these are commercial low-gravity solids. We also have commercial high-gravity solids. And for the most part, with very few exceptions, these are inert. Means they're non-reactive. They don't add anything chemically to our system. And the most common example is, of course, barite, barium sulfate. We add it for a weight material. Somebody has paid for it, so it's commercial. It's a high-gravity solid. It comes in at about 4.2 specific gravity. It is inert. It doesn't react with anything. And so we put it into that category. If we flip to the other side, we talk about these formation solids. And again, formation solids are solids that we generate during the drilling process. They are generated from downhole. We do put a category around formation solids on the high-gravity solids. They are not common, but there are some areas of the world that we drill where we will drill into barite stringers, hematite stringers in the formations. But they're just not very common. But we do put a little box there just to be able to note it is possible to have a formation solid, right? We generate and we mine barite and we sell it in the industry, but it does come from the formation. So we do put it there. We also have formation low-gravity solids. And this is an important distinction that I want to make sure that we all are following on this particular category. When we talk about low-gravity solids, in the formation, we have reactive low-gravity solids and non-reactive, just like we had with our commercial solids. On the reactive side, these are bentonitic clays. These are clays that we pick up from the formation. We may drill a clay stringer, or perhaps you're drilling through a shale formation, and we have clays that haven't yet gone through the entire process of diagenesis and formed into a shale. And so they're these clays that sit into the interstitial areas of the formation. We do pick up bentonitic clays, and as we'll talk about, there's a lot of areas of the world where many times we could start drilling with just pure water, and we pick up clays, and we will build viscosity. We will build wall cake as we go on. And then, of course, we have the formation low-gravity solids that are non-reactive. These are our bad low-gravity solids. And the most common is we throw these into a larger group, and we call them drill solids. They may be shale particles. They may be quartz. They may be sand. They may be mica. They may be any of these different types of formation, pyrite, that we would drill, and they are brought into our fluid system, and they create a negative purpose for us, so that there's nothing beneficial about them. They're non-reactive. They don't build wall cake, and they can't help us increase viscosity that we want. And so those are generally what we term bad low-gravity solids. We want to remove these solids out of our mud system at the first available opportunity. They have no benefit to you other than causing you a whole lot of problems later on. So that's kind of how we want to look at it from a tree of commercial and formation solids, both low-gravity solids and high-gravity solids, reactive and non-reactive. And so we'll come back to this chart and talk about it a little bit more here in a bit. But when we talk about these, we also want to mention what their specific gravities are, because they play a critical role in our fluid system. And so when we look at it, we can basically take our entire chart that we've already mentioned, and we're going to drop it into a little bit of a timeline. But instead of a timeline, this is a specific gravity timeline. When we look at specific gravity, we start over here on the left-hand side. We know that water has a specific gravity of 1.0, right? As we move closer up the specific gravity line, and we get to about 2.6, we find bentonite, sodium montmorillonite, which is a low-gravity solid, but it is a good low-gravity solid. Many times we will commercially add it, but as we just pointed out, some of it may come from the formation as well. Most of your drill solids will also fall somewhere between 2.6, 2.7. Every once in a while, you'll get up to about 2.8 specific gravity on your drill solids. But they do sit on that lower end. And then, of course, as we move our way further up, we get to barite at 4.2. And then hematite, if you happen to be drilling with a hematite-weighted mud, at 5.0. Over on the far right side of your chart is, of course, steel. Steel comes in at about 7.7 to 7.8 specific gravity, depending upon the oxidation state of the steel, on the very, very high end if you happen to be working in a milling operation, or if you're drilling a window to do a kickoff, something like that. And so when we look at solids and we look at all the solids in our fluid, it makes sense for us to say that the average specific gravity of all the solids that are in your fluid should sit somewhere between 2.6 and 4.2, unless, of course, you're weighting up with hematite. But let's set that aside for just a minute, and let's assume that you're weighting up with barite. The average specific gravity of all the solids in your drilling fluid should sit somewhere between 2.6 and 4.2. Now, I share that with you as a little bit of a golden nugget to keep in the backside of your minds. As you're reading through mud reports and you're looking at mud properties, or somebody hands you a mud report and says, hey, what do you think about this? Always look at the solids. Mud engineers will generally put the average specific gravity of the solids toward the bottom of the mud report, and it'll either say ASG of the solids, or it'll have solids, and then beneath it in a subscript ASG. Always look and see what their calculated ASG is. It should almost always be between 2.6 and 4.2. If you ever look at a mud report and you have an ASG that is outside of that range, you really need to take a close inspection of that mud report and really talk with that mud engineer to understand why the ASG of your solids is outside of the range. And there very well may be a good reason. Perhaps you're weighting up with hematite. Perhaps you just got done with a milling operation and they picked up a lot of steel particles in the mud. Whatever it is, just always be aware of that. But your average specific gravity should generally be between 2.6 and 4.2. If not, that should send up little yellow flags in your mind. Hey, I need to take a look at this. I need to understand why these are different and what the change is. And so from a specific gravity standpoint, that's generally what we look at. And we really want to take a look and be mindful of this box, this range of specific gravity of solids. Almost any mud engineer you talk to will tell you, yes, specific gravity got to be between 2.6, 4.2. And I'm going to show you why here in just a little bit with some calculations. So I'm going to go ahead and move on a little bit. We also classify solids by size. And this is just a standard chart that shows the different micron size of our solids, typical solids that we find in a drilling fluid, along with the API screen mesh. As most everybody is aware, 6-7 years ago, we went to a consistent screen mesh size designation by API, and I believe it was in 13B. And so I've included that here for you, as well as what the diameter is in inches. And so as we look at this solids classification size, this becomes very important to us when we start talking about solids control, solids removal, moving these out of our mud system. And as I've mentioned, the primary location that we want to move the solids out of our mud system is at the shale shaker, the very first available opportunity. And this is important to us because what we do not want to do is miss the opportunity to remove bad low-gravity solids, that is, non-solubilized, non-reactive solids, solids that do not do us any benefit in the system, and have a chance for them to be degraded in our mud system. Or said a little bit differently, those solids to be broken up over time into smaller and smaller pieces and recirculated. This is one of the worst things that you can do with your drilling fluid. And I spend a lot of time, and I emphasize this to you with a lot of passion, because you have to understand what happens to that solid. As a solid particle gets broken up into smaller and smaller pieces, as you can see from this chart, we're breaking it up, and there is now an increase in surface area. Anytime you have an increase in surface area, you have an increase in pump pressure, because it's taking more force to move those solids up in the wellbore. So you have an increase in pump pressure. As we talked about, you have an increase in ECD. You have more fluid loss going to the formation, increased chance of differentially stuck pipe. And as the solids get smaller and smaller, it becomes more difficult to remove them. And so these smaller particle sizes then, if we think about it from a solids control standpoint, ideally on this little chart with these few graphics that I've included for you, we start on the left-hand side with, of course, our shale shaker. That is where you want to get out the majority of your solids. On a water-based system, it is very, very, very important that we do it at the first available opportunity. Then we have a desander unit. Here are the second one in our order. Behind that, we have a desilter unit, and then we have a centrifuge. And if you look at this, I put a little bit of a line, 2 lines down here at the bottom. From left to right, it is easier to remove solids in a shale shaker, and it is harder to remove solids in a centrifuge. They're very efficient. You can do a great job with centrifuges, but overall, with all the solids in our system, it's a lot easier to take them out at the first available opportunity and do what we're calling screening up in the system. Also, what we see is when we look at the solids control process with our few examples we have here on the slide, from left to right, we also have the lowest cost to remove them, the lowest maintenance cost. By getting them out at the first available opportunity, we don't allow them to degrade, we don't allow them to break up into smaller pieces, we get them out of the system versus moving over here to the right-hand side where we have a higher maintenance cost and a higher cost for some of this additional equipment to be brought out to the rig, to be set up, to be reprocessed. Many people often ask me at this point, well, this is great for water-based, Kevin, well, but what about when we have oil-based mud? Well, very good question. Remember that we will not run a desander and a desilter, but we will run what we call our dual centrifuges or barite recovery centrifuges. And we run those to help keep the barite in the system. We separate out the low-gravity solids and our slurry, our expensive base oil. We recover that, and we remove the low-gravity bad solids out, returning the base fluid, the base slurries, back to our system. So very, very similar type of operation. So question then, why is it the bad practice to wait up with drill solids that aren't removed from the mud? And I stop with this slide for just a moment. This is the most common question I get as I'm at a drilling rig. I'm talking with well site supervisors. I'm talking with drilling engineers. And the question says, well, let's just save money on barite and let's just wait up with drill solids. Let's bypass the shakers. That is one of the worst things that you can do in your system. You want to remove the drill solids out of the mud system at the soonest available opportunity. Remember, as I said before, they are non-reactive. They don't help build wall cake. They don't help with viscosity. They don't help with gel strengths. They're not uniform as we think about a commercial solid, and thus they are very abrasive and they destroy pump parts. You're on a rig, if they're having to replace the liners quite a bit, usually it's because you have some very, very abrasive drill solids that have been incorporated into that. So it's always important to remove the drill solids out at the first available opportunity. If that means screening up, it's important to screen up. Get a smaller mesh screen on your shakers, get more of the solids out, have a cleaner fluid so that you can move to adding the chemical for the reactions. I have put a little bit of a chart here. Not going to spend a great deal of time on this, but just talking about some of the more common solids that we will add to the system, what their specific gravity is, and then what do we use when we begin to convert that from specific gravity to either pounds per gallon or if you're dealing in metric, kilograms per cubic meter, and then how do we convert that into pounds per barrel? And this is an important chart because as we start calculating the solids in a drilling fluid, we have to remember what the specific gravity is. And so as we look at this chart, and you'll have this in your notes, basically if you move all the way over to the right-hand column, that density in pounds per barrel, an easier way to say this is how many pounds of this chemical will displace 1 petroleum barrel of drilling fluid. How many pounds of this chemical will displace 1 petroleum barrel of drilling fluid? And so if you look at barite, we know that 1,472 pounds of this chemical displaces 1 petroleum barrel. So as we add more barite, we begin to weight up that system. We know how much of an increase we should have to the overall system. And then again, you can see the same with hematite, calcium carbonate, bentonite, and drill solids. So with that, let's talk about how we calculate solids. And I am going to provide you with a sample calculation. It will be distributed to you. Clay will send that out after the webinar today, along with the slides, walking through each one of these calculations and why we calculate them. So if you don't catch it the first time, I know I'm moving fast. I apologize for that, but I want to be able to get to the Kahoot at the end and kind of see where we're at with things. But basically, we want to calculate the solids in a drilling fluid because we have to know what our density is. We run a retort, and we calculate it with what we call a methylene blue or an MBT test, and what each one of those does. So first, with our retort, this is a diagram of a standard retort. This is a 10 mil retort. What happens in this 10 mil retort is we are going to put a sample of drilling fluid into the chamber. Your mud engineer will run this, and the fluid sample is cooked off. It is burned, and it is burned into a gas, which are then condensated back into as a liquid into your retort receiver tube, and we can calculate the different types of fluids that exist in that mud, whether it be water or whether it be a type of oil that is in that mud, and what those percents are by volume. We will then run a methylene blue test, and the methylene blue test is conducted by methylene blue dye. And what we are doing is we're adding a sample of this methylene blue dye into our fluid system, and we are allowing it to cook, we're allowing it to mix, thus it's exposing all the electron sites on the clay particles, and we're measuring how much of that methylene blue dye will be absorbed into or onto the clay platelets. That means how much will they take in. And it's what we call a cation exchange capacity. So many times you will see your mud engineer, they will have a little piece of paper like this on filter paper with little blue dots on it around their mud test equipment. And essentially what they're doing is they're measuring how many mils or what volume of dye it takes to create this little halo that you see right here at 6 milliliters. And so we measure that, we find out what that volume is, and from that we can calculate the concentration of reactive solids in our fluid. How much is reactive? How much can we use to build viscosity and to be able to build wall cake? And so there's our cation exchange capacity. We measure it in bentonite equivalent pounds per barrel. And if we know how many pounds of the bentonite equivalent that we have, we can calculate it from our cation exchange capacity for each type of clay individually. Sodium montmorillonite happens to be 5. We multiply that by 5, and we could calculate the pounds per barrel of equivalent clay. So 5 times 5 in this case, as an example, means we would have 25 pounds per barrel of equivalent clay in the system. And we talk about this more in the Drilling Fluids Technology course. Or if you have a further question on it, please reach out to me. I'll be glad to help you with it and answer any of those questions here toward the end of the webinar. So we use material mass balance, and I'm going to provide you with the equations. They are here as well as on the sheet that will be distributed to everybody. So if you don't have them, don't worry about writing them down. You'll get all of these. But we calculate the average specific gravity of the solids in our mud. That's what the ASG stands for. The volume, we do it with the volume of mud that we have, the times the specific gravity of mud, minus the volume of water times specific gravity of water, minus the volume of oil times specific gravity of the oil, divided by the volume of the solids that are in our fluid. And so we will calculate that. Then we will calculate the percent low gravity solids, and I provide the equation for calculating this, along with the pounds per barrel of low gravity solids. And all of your mud engineers on location should do this every single day. This is very, very important because this tells you what kind of low gravity solids percent by volumes and high gravity solids percent by volumes that you have in your system, and you can make a better estimation as to whether or not you're taking care of the solids. Are we removing it out as efficiently as we should be? And here is the calculation for percent by volume high gravity solids, your pounds per barrel high gravity solids. And then, as I mentioned previously with our MBT, we will calculate our equivalent bentonite content, how many pounds per barrel that we have in the mud. And keep in mind that just because you have put 20 pounds per barrel of commercial bentonite into your mud for viscosity and filtration control and to build wall cake, you may actually have more than that in your system because you may have picked it up from the formation. So it's helping you provide some of that filter cake and providing that viscosity for you. From there, then, we can calculate how much drill solids we have. We know how many pounds per barrel of low gravity solids we have. If we subtract the bentonite equivalent from that, we know everything else must be the non-reactive or the bad low gravity solids in our mud. And so we put all of that together, and I've got a little sample calculation for you. This, as I said, this will be distributed to everyone on the call. Clay will send this out along with a copy of the slides. And I put a little bit of a quiz in here. You can kind of test your knowledge. And I'm asking you to walk through the different calculations that every mud engineer does every day at the well site. Calculating the ASG, calculating the percent low gravity solids in the fluid, the pounds per barrel in concentration. Then we will do the same for high gravity solids. Then we'll calculate the bentonite equivalent, and we will also calculate the drill solids that are in the fluid. Down at the bottom, I give you a little bit of a help, giving you the mud weight. I gave you the retort oil, the retort solids, and then our specific gravities we have in the system, along with our bentonite CEC and the density of water. A little bit of a trick as you walk through it. Don't cheat. Don't scroll to the bottom, but I also gave you the solution to the problem. So test your knowledge, do your own calculations, see if you come up with the same answers as you go forward from it. So the question comes up is, okay, Kevin, well, what do the calculated values tell us, and what do we look for as good? What does it mean to have a good solids content? So let's talk about total solids right now. Number one, we need the solids content to be as low as possible, but we want to make sure we are maintaining wellbore pressure, right? We add barite to the system to hold back formation pressure. We maintain that wellbore pressure, so it's strictly dependent upon mud weight. We have to make sure we have well control. The majority of the solids content should be high gravity solids or barite in a weighted system. That is high gravity solids. And you know how to calculate it. I gave you the equation for it, and it'll be also on the cheat sheet, which we will distribute to everyone. The average specific gravity of solids in your mud, overall solids, should be greater than 3.0 for a weighted mud. Because remember, as you're adding barite to the system, your ASG should slide to the right. That it should get closer and closer and closer to 4.2. The ASG of the solid should be greater than 2.5 for an unweighted mud. There's no barite. I don't have any problem with having an ASG 2.5, 2.6, all the way up to about 2.8. But the trick then is, what is the concentration of your low gravity solids? And you would have calculated that. Always try to maximize your solids control equipment, especially on your water-based mud. Screen up whenever possible, as long as you're not losing mud over the end of your shakers. Depending upon your pump rate, depending upon how fast you're drilling, what the volume of solids is that's coming off the end, always try to maximize the screens, going to a smaller mesh screen, getting more solids removed off the end, and having a cleaner fluid. Also, in your water-based mud, run your desander and desilter as often as you can. Especially if you're not weighting up with barite. That way you're not removing any of it out of the system. And if your system affords it, if the operation allows it, run your centrifuges. Your centrifuges help to remove the very ultra-fine low-gravity solids, stuff that the shale shaker, the desander, the desilter may not be able to remove. So let's talk about drill solids. Remember, these are the bad ones. These are the foes, as we talk about in the title of the webinar today. They are bad low-gravity solids. They are abrasive. They're difficult to remove. In a perfect world, I'd say remove all of them. But that isn't always the case, and we usually have a little bit that is left in the system. Try not to ever let your drill solids get higher than about 6 to 7% by volume. I prefer much lower, 3 to 4% by volume, But if you have to, never ever let it get above 6 to 7% by volume. And then I will dispel the myth. Dilution is never the solution. I've talked to a lot of people that say, well, we'll just add more water to the system. We'll dilute back our solids. Think about the fact that every time you add another barrel of water into your mud system, that means you're also having to add another bit of chemical for every barrel of water added. So it's costing you more to dilute back your system than it is just to remove the solids in the first place, especially on some of your more advanced fluid systems where a lot of these chemicals are not cheap. Dilution is not the solution, and you need to be very careful about that. On the reactive low-gravity solids, remember, these are the good ones. These are your barite, your kaolinite, your illite clays, any of them that are reactive. It'll help us build that viscosity in the system. We measure it with the methylene blue test. The mud engineer should be able to provide you with the methylene blue that could show you the little halo that's out there. Always ask about it. I always like to run my mud system somewhere between 20 and 30 pounds per barrel of bentonite. I'll go higher than that depending upon the type of filter cake I'm going to run, and then I'll back off a little bit as we get closer to total depth and we start to run our casing strings. Always want to maintain a good yield point. Make sure that you have a good carrying capacity, but when you get to the bottom of the interval, you're going to bring your gel strakes down, decrease it with a thinner to be able to run pipe. And remember that if you're adding base fluid to your mud, whether it be water or for oil-based oil, you have to compensate with those bentonite concentrations. Otherwise, you lose your rheology and you've diluted back and you've defeated all the stuff that you've added to your mud system to begin with. Your high gravity solids, very important that when you are running a weighted mud system, the percent by volume high gravity solids should be very, very close to what is calculated. What do I mean by calculated? I mean, if I add 20 pounds per barrel of barite to my system, I know how much barite I added, I know the volume of my system. Then when you run your test and you calculate out your high gravity solids, it should be pretty close to what you actually added to the system, unless you drilled a barite stringer, right? That goes kind of without saying, but always be aware of that. Kind of do a quick check. It should be pretty close. Maybe not exact, but it should be within a pound per barrel or two, depending upon the mud system that we're running. So those are kind of some high-level thoughts on solids. I know we covered a lot. We covered it very, very quickly. Let's talk about what we've learned. So we're going to play a little Kahoot quiz. If you've played Kahoot, you're very familiar with this. What I need you to do is, if you're going to play along with us, open up a browser window, either on your smartphone or your computer, however you're joining us on the webinar today, and go to kahoot.it, kahoot.it, and then hit enter. And it's going to ask you for a game pin, and you can enter this 2382349. It will ask you to choose a nickname to play the game, and I'll issue a very friendly caution to everyone. Please be polite, professional, and respectful with your nickname, and know that everyone is going to see your nickname. So choose something you don't mind everybody seeing. Don't put your own name if you don't want to. Just choose a name in there if you'd like to play with us, and then stand by. I'm going to give a minute or two for everyone to join, and then we'll move through. You get more points the faster you answer the question correctly. If you wait too long, you get lower number of points. Make sure you read the question, then answer on your device, and I will say good luck. So I'm going to move my Kahoot over here real quick. And here we are in the game. I hope everybody can see our screen okay. Clay, give me a thumbs up if you see it.
Yep, looks good, Kevin.
All right. I see a lot of people joining. Very good. Somebody joined as me, which is great. Looks like we got about 15 people in, 16. If you're going to join us, please go ahead and join us. Again, kahoot.it. The game pin is at the top. Join us pretty quick here, and we're going to get started. I want to be respectful of everybody's time. Again, give you another 20 seconds or so. Looks like we got about 19 joining us. Like it slowed down a little bit. There's the 20th one. Okay. Oh, we got one more, 21, 22. All right. Well, I'm going to go ahead and get us started here. So again, you get more points for quicker answers. There are 15 questions, 15 questions. Make sure you read the question, very, very important, and we will get started. So when you read the question over on my screen, you can answer on your smartphone or on your computer. Make sure you look and see which answer is which on your phone so you select it correctly. And here we go. Question number 1, what is the impact of increased solids content on the rate of penetration while drilling? You got to be fast. We're going to move through this pretty quick. What is the impact of increased solids content on the rate of penetration while drilling? All right, time's up. I have 16 people that says it decreases the ROP. Very, very good. I've got 5 people that says it increases the ROP, and 1 person said there's no effect. Remember, as you add solids to your fluid system, it will decrease your rate of penetration. It slows it down because the fluid doesn't pump as fast. You can't drill as fast. The drilling rate is very grainy, as we call it in the fluid business. All right, let's go to question. Oh, I'm going to have a scoreboard. It looks like JJ answered the quickest. He's got 933 points. Kevin's at 908. Mukesh is at 895. So here we go with question number 2. If we increase the solids content in a drilling fluid, surge and sob pressures while tripping will decrease. True or false? If we increase the solids content in a drilling fluid, surge and sob pressures while tripping will decrease. You got about 5 seconds. We're moving on. All right. I got 17 people that said false. Very, very good. That is the correct answer, right? Surge and swab pressures will increase as we increase the solids content in a fluid. Scoreboard check. Looks like Kevin has taken over the lead with 1,886 points. KNP's in second with 808. And PAPUL is 1,798. Here we go with question number 3. Barite is an example of, is it a low-gravity reactive solid? Is it a low-gravity non-reactive solid? Or is it a high-gravity reactive solid? Or is it a high-gravity non-reactive solid? You got 5 seconds. Answers coming in. All right, almost everybody agreed. It said it was a high-gravity reactive solid, and you are correct. It doesn't do anything. Barite does not build wall cake. Barite does not help with viscosity. Now, if you make the argument and say, well, it helps to increase when we pump sweeps, and we have weighted sweeps. Remember that we're dealing with surface area with the barite. You're not dealing with the viscosity of the barite. Difference completely. All right, so scoreboard, PAPUL is taken over, followed by B1 Birdman 4. All right, next question. Here we go. Question number 4. Which of the following is an example of a low-gravity reactive solid? Questions are pouring in. Got about 10 seconds. Remember, an example of a low-gravity reactive solid. Low-gravity reactive solid. All right. Bentonite clay. It is our prime industry example. Absolutely, that is a low-gravity reactive solid. Drill solids are not reactive. Drill solids. I didn't say bentonite from the formation. I said drill solids. Very, very good. 16 of you got it right. Let me get my cursor here. And the scoreboard. PAPUL is still in the lead, followed by the Birdman with a 1 and a 4. Next question. The average specific gravity value of 5.6 is acceptable for a water-based drilling fluid. The average specific gravity value of 5.6 is acceptable for a water-based drilling fluid. Normal conditions. Do we like to see 5.6 on an ASG? All right, I had 17 of you that said false. That is absolutely correct. Even if you're drilling with hematite-weighted muds, it shouldn't be any higher than 5.0. And there's hardly any fluid systems in the world where you're weighting up with pure steel. So that is absolutely correct. The answer is false. Scoreboard, looks like PAPUL is still in the lead with 45.73. Let's go to the next question. Question number 6. A drilling fluid which has a density of 14.2 pounds per gallon should have an ASG of the solids greater than 3.0. Oh. This is an interesting question. A drilling fluid that has a density of 4.2 pounds per gallon should have an ASG of solids greater than 3.0. And I had 20 of you select true, and you're absolutely correct. Remember that even low gravity solids have a specific gravity of 2.6, which is about 21.697 pounds per gallon. So yeah, all of those solids are going to weight up your system, so the answer absolutely is true. All right, check on the scoreboard. PAPUL is moving ahead here by almost 100 points. Here we go. Question number 7. Which of the following is true about a good range for ASG of solids in a drilling fluid? What is a good range for ASG of solids in a drilling fluid? Of all of those options, what should we see? All right, I've got about 20 of you that have selected the orange one here. You're absolutely correct. 2.6 to 4.2, generally speaking. Again, there are some exceptions to it, but by and large, when you look at a mud report, the ASG of the solids should have between 2.6 and 4.2, unless there's some really strange circumstance. All right, check the leaderboard. Oh, it's getting closer. First and second place are only about 20 points behind. Here we go. Next question. What is the most accurate diameter micron size of clay colloidals in a fluid? What is the most accurate diameter and micron size? I didn't say specific gravity. I said micron size of clay colloidals in a drilling fluid. All right. All right. I had 13 of you say about 5, and you're absolutely correct. Really, somewhere between, I could have said 1 to 5, 5 to 10, 1 to 10, 1 to 15. Very, 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 very low. All the rest of the answers were well over 100. Those aren't clay colloidals. Those are our API sand-sized particles. Your colloidals are very, very low. All right, check on the leaderboard real quick. Oh, we have a new leader in the clubhouse. Mamin has taken over the lead. Next question, number 9. Which of the following is true about a retort analysis? What is true about a retort analysis? Lots of good answers there, but there's one that's better than the rest of them. All right, question number 1. A retort measures the percent by volume of oil and water in a system. You are absolutely correct. To the 16 of you that answered it, well done. The rest of these, it measures water and oil, so 2 of the answers are wrong. And remember, the solids aren't measured, but they're generated. We know those as a difference. So, looks like Birdman is kind of taking this over. 78-48. 5 more questions. Here we go. Question number 10. The methylene blue test measures. What does a methylene blue test measure? What does it measure? Remember, we talked about the cation exchange capacity. All right, I got 14 say good reactive low gravity solids. Well done. Absolutely. Remember, it measures the reaction when the clays react with that dye, and they both adsorb and absorb the dye onto the clay particle. All right, leaderboard. The Birdman is climbing ahead here, about 300 points. Next question. Question number 11. In a weighted mud system, the majority of solids content should be high gravity bentonite. High gravity bentonite. Be careful with your answers. I got 22 already answered and said, hey, I got this. False, right? Which should be low gravity bentonite, but in a weighted system, most of the solids should be your barite, right? Because now you're going to have a higher ASG in the system. You'll still have some clays in the system, but by and large, the majority of them should be the barite that's in the system. So looking at the leaderboard, we still got, looks like Birdman in the lead, followed closely by Kevin. Next question, number 12. The overall concentration of drill solids in a drilling fluid should never exceed 6 to 7% by volume. Should never exceed 6 to 7% by volume. Okay, we're coming down to it here. I got 23 answers in. 22 people say true. Very, very good. Excellent. You are correct. Oh, getting close here. We're about 900 points difference between first and second place. Here we go. Next question, number 13. What's the best type of solid to have in a mud system while drilling? I mean, what do we want to have? What type of solid do we want to have in a mud system? And you could say the entire, encompassing the entire operation, right? Filter cake and everything else. Right, you want reactive low gravity solids. Now, you say, well, Kevin, what about in a water-based or an oil-based mud? Remember that even in a water-based mud, you're still building filter cake. Oil-based mud does build filter cake. It's just organophilic clay that we are using, or clays that have been treated with an amine to be able to react with oil. All right. Check on the scoreboard. Looks still close, about 800 points difference, first and second place. Question 14, only 2 more to go. The concentration of high gravity solids in a fluid should be very close to the concentration of barite added. This one should be pretty easy. We just talked about it. Should be very close to the concentration of barite added. 4 seconds. Absolutely true. Absolutely true. Realistically, your barite won't come from any other place, and there's nothing in the system to contribute to the concentration. Absolutely, it should be almost exact. I mean, it may be a pound per barrel off by calculation, but that's because we have a calculation problem. That's not because of the physical condition of the fluid. All right, moving in on our last question. Looks like I guess his Birdman with a 1 and the 4 is running away with this thing with 1,100 point difference between first and second place. Here's our final question. Bentonite clay has a higher density than barite. Bentonite clay has a higher density than barite. Wow, it's only 22 answers already. We still have 10 seconds to go. Bentonite clay. Well, we know bentonite clay. Bentonite clay has specific gravity of 2.6. Barite is 4.2, so that answer is false. Very, very good. All right, we checked the podium. Third place was PAPUL. Second place was Kevin with 12,081. And first place, those two, Birdman with a 1 and the 4 in their name. So congratulations, well done. Great job on that. Y'all did a very, very, very good job. So with that, we're running a little bit over, but I want to open this up for questions. So Clay, if you'll kind of take us over from there, we will address questions.
All right, thank you, Kevin. I do have a few questions here that came in during the presentation. Again, if you want to get your questions in, we still do have time, so type them into the chat there. So to start off, a couple of oil-based mud questions. The first one says, do the same concepts around solids analysis work with oil-based muds?
It does. We use the same calculations, but also keep in mind that around oil-based mud, we typically have more barite in the system. We typically use oil-based muds, deeper depths, which means we'll have more barite, which means your 4.2 gravities will be affected. We run the same equation. The difference, though, with oil-based mud is that we do not run a methylene blue test or an MBT test on oil-based mud. It doesn't come out right because the dye is affected by the oil content. But from the calculation standpoint, yes, it is the same.
Okay, so then the next question says, why are desanders and desilters not used in oil-based muds?
Great question. So desanders and desilters, remember, are primarily used for water-based muds. Normally with an oil-based mud, we have barite in the system, and your barite will be discharged by the desander and the desilter if you are running them. The second reason we don't run those in particular is because many times your oil-based muds will clog up the orifices on the bottom of the hydrocyclones on both of those, and they're really, really tough to keep clean. However, we do in oil-based mud, as most of you know, use instead a mud cleaner, which is essentially a desilter which has been put on top of a shale shaker in order to recover back the barite or discard the low-gravity solids and keep all of the high-dollar fluid that we would be added into it.
All right. The next question here asks, what are the main factors used in selecting mesh size for the shale shaker?
Sure. So when you're selecting mesh size, and keep in mind that, like I said, about 6-7 years ago, the industry formalized the approach on how we name shaker screens. Prior to that, there was many different screen providers who had different size wires, they had different shaped mesh, etc. And API has gone to, and everybody has adopted, using a universal tag for distinguishing what size solids are removed. Specifically, we're talking about our D50 cut point, where 50% of those solids are removed out of the screen. So the question then is, you know, when we talk about mesh sizes, realistically, it depends upon what you're drilling, the hole size. It also depends upon how fast you're drilling, and it also depends upon the type of fluid that you're running. If you're drilling a surface hole where you're drilling very, very fast hole, lots of solids coming through, we may be running a 210 mesh, we may be running a 180 mesh, something like that. But again, the key point is to be able to run as fine a mesh as you can to remove the most solids as you can out of your system and keep the fluid and keep all of the reactive solids that are more into the fluid already and have already been dissolved into the system.
Okay, and then a question on a similar topic. It says, I drilled a chalk formation with WBM, I'm guessing that's water-based mud, and the MW went really fast. So which size of screens would you recommend? So
you're talking about drilling chalk wells, heavy alkalinity, heavy lime content, which means that your pH is going to come into play very quickly here. And what I mean by coming into play is, remember that when we want to viscosify a fluid, you are heavily dependent upon having a alkalinity, a pH of the system to expose those electron sites on the clay platelets when we're talking about clay chemistry. So when you're drilling a chalk, you're drilling lime formations, and those lime formations have natural alkalinity associated with them, which means your fluid has a tendency to get thicker much quicker in the drilling process. So when you're talking about screens and being able to screen up, It depends upon the size of the hole you're drilling. Are you drilling an 8.5-inch hole? You're drilling a 6 5/8-inch hole, realistically, and how fast are you pumping? What is the pump rate? How are the screens managing it? One of the secrets to being able to manage drilling most of your chalks and screen size is if you start off with about 210 mesh screen, let's say, and you start to have a whole lot of plugging going on because that fluid's coming back very thick and it's coating those screens, and you're running a water-based system, you can use water and be able to spray them down. You're adding water to the system, so you're still building volume, and you're still allowing a lot of the bigger solid particles to come out. But that's one of those chemical reactions that you have to monitor very, very closely because how thick that mud will get. The second problem that you have with it is flipping that mud system, right? You drill so much of the chalk, so much of the lime-based alkaline nature, you're exposing all of these clays. You have to be careful on how much clay you add to that system to help your viscosity and to help your filter cake. But starting off, say, with about a 210, if it can't handle it, you can wash them down. If you can't keep up, you need to go to a larger mesh screen.
All right. Next question says, what is the effect of well angle on solids accumulation in the fluid system?
So solids stimulation in the fluid system?
Solids accumulation.
Oh, solids accumulation in the mud system. So great question. So when we drill high angle holes or horizontal holes, remember that solids are going to be pulled with gravity. So solids will begin to fall to the bottom of the wellbore, and as such, we begin to build cuttings bed. The most critical area for circulating solids out of a deviated wellbore is in the angled section. Usually what we call it is somewhere between 40 and 75 degree angles. And the reason being is because even as we're pumping sweeps, we're pulling solids out of that the horizontal section, and as we get to that deviated section, the fluid profile, the fluid dynamic starts to change. It moves from a laminar flow pattern to a turbulent flow pattern. And because it is not consistent, solids have a tendency to fall out, and they start to build these cutting beds in those areas. And so that is why whenever we want to drill these deviated well bores, we typically want to pump a sweep with them, either a viscous sweep, or if you're trying to push them as far as surface area with a weighted sweep. I'm more fond of the viscous sweeps myself, gel sweeps, polymer sweeps, to be able to clean out those deviated angles. But those are the biggest challenges in hole cleaning. Gravity's pulling the solids down. Deviated hole angle, the solids have a tendency to build those cutting beds in that angled section.
All right, and then we'll have one more question here. Now, there were a couple questions that came in that were quite long, and so we will address those offline. Again, we want to be respectful of everyone's time, so if we didn't get to your question, just know that we will answer it, just not during this session. So the last question we'll get to today says, when a methylene blue test is performed at the well site, why is barite not measured in that test?
Great question. So when you run the methylene blue test, remember that the methylene blue dye that we're dropping into the Erlenmeyer flask when the mud engineer is boiling it is trying to reach out and become adsorbed and absorbed onto each one of the clay platelets. Barite is inert. So the methylene blue dye doesn't affect barite, it doesn't pull it in, and it has no effect on the test. All we are measuring is the reactive clays. And the methylene blue test is a critical test. It's one that many times people maybe want to skip over for sake of time. They got to boil the sample in this, but it is probably one of the most critical to understand the actual condition of the fluid. Barite's inert. It's not affected by the dye.
All right. Thank you, everybody, for the nice, thoughtful questions. And Kevin, thank you for your answers and for an awesome presentation.
Sure. And just a note to everyone, on my slide here, I've put my email address here at PetraSkills. Please feel free to reach out to me, and I will answer any of those longer questions as Clay has noted, and we'll get back with you ASAP on those. But please reach out to me if you have any questions, mud, solids, etc. Be glad to help you out. So thank you all very, very much, and y'all have a wonderful rest of your day.
Thanks, everybody. Take care.